So what we're talking about today is section 2.5, continuity. And so um, continuity is a property of functions. Continuity is our first property. Let's see if I can spell. Is our first property about functions that uses the limit. Let's see why. So just intuitively, what is something that's continuous? Something that's continuous intuitively has no breaks or jumps or vertical asymptotes, say. And so let's put that together intuitively. A function, if I can say that, is said to be continuous on some domain. The domain is important, by the way. On some domain, if you can draw its graph without lifting your pencil. Now I have to really emphasize that this is intuition, right? This is not how we're actually going to prove that something is continuous or not continuous, but you can use this as a general idea. And so just as a couple of quick examples, this would be an example of a continuous function. This would be an example of a function that is not continuous here at 0. So notice, by the way, that if you were to consider the domain to be all x such that x is not equal to 0, then the function actually is continuous on that domain, right? Because I removed the bad point. Let me say that again. So on this graph, right, if I were to draw this graph, I would have to lift my pencil to get from like here to here. However, if the domain skips the point 0, then your pencil has to skip the point 0 too. And so once you're finished with this one, you would stop, and then of course you would never finish. But if you were to finish, then you would skip over 0 because it's not in the domain, and then you could draw that. Okay, what else is there? How about something like this? So that would also not be continuous at this point. And then, of course, if you wanted to get real wild here, we could put some points in here. Okay, that wouldn't be continuous anywhere. These aren't actual curves there. These are single points. So if I just had a random smattering of dots, right, that would not be continuous anywhere. Okay, of course we don't need it to look like that, but we'll save that discussion for later. Okay, so we want to avoid all these cases, right, in order to be continuous. And so what do we need for the function to be continuous? In order to avoid this situation, we need that at all x, or let me say x equals a, the limit as x approaches a of f of x must exist. Okay, but that's not quite enough, because here's an example where the limit does exist, but would this be a continuous function? I think you would agree that it's not. And so not only must the limit exist, but is it enough to say that f of a exists? Oops. Not by itself, although that is a condition, right? Because the function needs to be defined everywhere on its domain, and so everywhere where the function will be continuous. And so the point that I want to make here is that this solid dot has to be the same thing as the limit. Okay, if that is true, then we will say that the function is continuous at a. So let me summarize all that mess with a formal definition. Definition: a function f of x is said to be continuous at the point x equals a if the limit as x approaches a of f of x is equal to f of a. Okay, now be careful with this. This is the definition, but this implies that three things are true. One, the limit exists. So we have to be able to take the limit as x approaches a of f of x. Two, f of a exists. And just like we said before here, number 3, the value in number 1 has to equal the value in number 2. In other words, the limit as x approaches a of f of x must be equal to f of a. So when something is not continuous, that usually means, or that will mean, that one of these three things are not true. So not continuous means at least one thing here, one statement here, is not true. Okay, so let's take a look at our previous examples over here. So geometrically we were talking about this function. Okay, why is this function not continuous on the reals or not continuous at 0? It's because the limit does not exist. Okay, why does the limit, or sorry, how about this function at this point a? Right? In this case, the limit from the left exists, the limit from the right exists, but the limit overall does not exist, right? And so that's why this is not continuous. And then this point down here, right, the limit exists, f of x exists, or f of a exists, but the two things are not equal. So this is number 3 that's not true, right? And this is number 1, the limit does not exist. Good, all right. So we'll try a few more of those. In fact, let's see if we can draw something from one of the homework problems. Oops, let me see if I can get the right color going there. Example is 1 minus x squared continuous. Let me not stop there. How about the absolute value? Well, let's see. What does that look like? Well, 1 minus x squared, this, let's see, this would be x squared, right? And then this would be minus x squared down here. And so what would minus x squared plus 1 be? It'd be this graph, right? And so let me erase the other pieces here. Just keep the relevant piece. And now where are these points? Right here. Those are at where the function is 0, so that's at plus or minus 1. Okay, and so this is the graph of 1 minus x squared so far. And so how would I get the absolute value from that? I think we graphed these before. This part stays the same, right? But then this part gets flipped, and this part gets flipped. And so if we were to write the definition over here, f of x equals 1 minus x squared if x is between or equal to, we could say, minus 1 and 1, and then it's minus 1 plus x squared if x is less than minus 1 or x is greater than positive 1. Good. And so the only possible point where this may not be continuous would be at the points plus or minus 1. But we can see here, and we can see here, what would the limit be as x approaches 1 of f of x? Well, it's going to be 0 no matter which way you go, right? Because you would take it from the positive, or from, if x is less than 1, you would use this formula and you get 0. And then if x is bigger than 1, you would use the bottom formula and you would also get 0. So the limit is 0. Then what is f of 1? This formula says to evaluate f of 1 in the first, using the first formula. So that is actually equal to 0. And because these two things are the same, so this is continuous at x equals 1. And so you could do the same reasoning, at x equals minus 1. Okay, we're going to take a look at some other examples in the next video.